All right, thank you very much, Rich, for that introduction. So like you said, I'm Tyler Leicht. I'm a PhD candidate working on amplified Northern Hemisphere persistent flow regimes and looking at them through composite analyses today. I'd like to briefly thank my funding source, which is through the Center for Western Weather and Water Extremes at Scripps Oceanography. So briefly, to motivate some of my work, I wanted to take sort of a somewhat real-time example of what I'm considering to be a persistent flow regime. So what we're looking at here is a GIF of some of Alicia Bentley's maps that was courtesy of Jay Cordera. This is looking at the 700 hectopascal geopotential height as well as IVT in both the shading and the vectors. This is from Christmas of 2022 through the 15th of January 2023. Now, as we can see, there's several individual cyclones that comprise this time period. So there's several events of cyclogenesis, the cyclone tracking across the North Pacific and interacting with the west coast of North America, where they got impactful rain and snowfall, especially in California. However, if you sort of zoom out, you can see that there's this larger scale structure of this dominating planetary scale trough that's spanning the entire North Pacific basin. So what I'm interested in is seeing how some of the variability on the synoptic scale can impact what we see in these large-scale flow regimes that seem to be quite impactful, as we can see here in the winter. Another brief bit of motivation is this is an email from Jay Cordera. This was sort of at the end of this large-scale regime. And in the center, they were tasked with informing people in the hydrology fields and other stakeholders in California about basically what happened throughout this period to make it so anomalous. So what I've got highlighted here especially is that there's these large question marks regarding what precipitated the persistent and sustained zonal flow across the North Pacific. So what allowed it to establish and what allowed it to break down, which occurred shortly after this email was sent. So clearly there's some stakeholder need for this type of information about large-scale weather regimes, and there's a lot of open questions still in the field about what are some of the underlying dynamics that contribute to the formation of these patterns. So briefly, just to do a bit of literature review on some of the dynamics that's already been established. So the sense of looking at weather regimes has been studied since the 1940s, especially by German scientists following World War II. There, it was typically a surface weather pattern organization through literal paper maps that they organized in different piles, and they came up with, at the time for Central Europe, about 29 familiar weather patterns. Along with that, there's also quite a bit of theoretical basis for a lot of these through idealized modeling studies, such as Charney and DeVore and Wallace and Gutzler in 1981. In terms of contemporary studies on weather regimes, they typically use either reanalysis or climate model output as the basis of their study, and they construct these regimes either through extracting leading modes of variability from EOF analysis. Occasionally, they'll use bandpass filtering just to extract the low-frequency variability, or they will combine similar synoptic patterns with clustering analysis. When it comes to the study of what makes the flow amplify at the large scale, especially during wintertime, there's many different mechanisms and studies that have tried to assess this problem. So there's been work talking about anomalous fluxes of vorticity that can help maintain a blocking high once it's been established. Both Rossby wave breaking and Rossby wave packets have been shown to either interact with a pre-existing block to sustain its life cycle or to contribute initially to the development of some of these persistent patterns. They're booing me off the stage already. Okay. Perfect. So along with that, there's also the importance of upstream cyclones in a lot of these processes, as they can both advect temperature and vorticity, both planetary and relative. Along with that, the storm track has a sort of self-feeding mechanism where it can redevelop the baroclinicity on the backside, as well as some of the characteristics of the jet stream. So looking at upstream diffluent flow patterns in the jet exit region can often prime a location for blocking in the next several days. And with that, there's also been consideration of, again, these Rossby wave packets and some of the slowdowns that can occur. And there's been sort of a traffic jam analogy that's been established by a few recent studies. Along with a lot of the mid-latitude processes that can occur, there can also be remote effects, especially from the tropical atmosphere and ocean. So that could be both El Nino Southern Oscillation, the Madden-Julian Oscillation, other sort of SST patterns that can occur on the seasonal timescale, as well as more local, smaller scale tropical convection. And that can have a similar impact to the MJO and typically can result in Rossby waves propagating through the North Pacific and interacting with North America. And lastly, just to bring it back to some of my own work, so Alex and I were both here last year and gave us a seminar on a lot of our master's work. And there I was tasked with specifically looking at persistent blocking over the North Pacific and Western North America. And from that result, one of my case studies that happened to be the longest lasting ridge over Western North America also featured this larger planetary sort of wave number 3 pattern that we can see here. So you've got sort of similar to what I showed in December 2022 to January 23. You can see this extended trough across the North Pacific, but then you've got blocking over Siberia, this large-scale ridge in the Eastern Atlantic, as well as the more meridionally oriented persistent ridge over Western North America. So from that, for my PhD work, I really was interested in sort of identifying these high amplitude, quasi-stationary, Northern Hemisphere scale persistent flow regimes, or PFRs, as you'll see me reference them later on. And I was interested in sort of analyzing how these persistent flow regimes can both form and develop. So for my methodology, in terms of identifying these persistent flow regimes, I used a modified version of Dolan-Gordon's 1983 criteria for identifying persistent anomalies. So this is a grid cell by grid cell criteria, rather than some of the other algorithms that have been proposed for looking at blocking specifically. This just takes into account the 500. Do not touch the wire. I think there's an Albany curse happening here at NCAR. So like I was saying, this only considers the 500 hectopascal geopotential height anomalies. So for this, I'm using standardized geopotential height anomalies from the CFSR. So that gives me 42 years or winters worth of data to use for this study. For this criteria, it must either exceed +1 standard deviation or be below -1 standard deviation for 7 consecutive days across the Northern Hemisphere. And I bound this from 20 north all the way up to the North Pole. From there, in order to assess the large-scale continuity of these types of patterns, I broke the hemisphere into 4 quadrants. I took the sum of the number of grid cells that met this criteria for both the positive and negative anomalies at each time step. And I consider it a hemispheric flow regime when at least 3 of the quadrants simultaneously exceed their local 80th percentile for the number of grid cells meeting this criteria. And this has to occur for at least 9 days so that there's a few consecutive days of this criteria being met at any given time. From this, these, again, flow regimes are saved if the duration is greater than 9 days. That resulted in 113 cases from the 42 winter seasons that I had. So roughly on the order of 2.5 to 3 events per winter season. In order to assess some of the variability and get a sense of what the common patterns are, these regimes are then aggregated using k-means clustering with 5 nodes. So here on the right is a typical method for optimizing the use of k-means clustering. It's called the elbow method. And essentially, you're looking for more of like a sharp inflection point in this sum of squared errors versus the number of clusters that you use for aggregating the data. In general, this wasn't a very conclusive optimization test. So from there, I used synoptic intuition, looking between what 3, 4, and 5 nodes resulted as the patterns. And I settled on 5 nodes just because each of the patterns resulted in some new variability being represented without necessarily degrading what the original patterns were in the 3 and 4 node options. And this has been done by other papers as well, looking at both atmospheric river families or Northern American weather regimes for k-means clustering. And so from this, I result in these types of patterns. So what we're looking at here is the 500 hectopascal heights and the geopotential height anomalies here in the shading. There's stippling to indicate statistical significance at using a student's t-test, and this is at the start time of each of these persistent flow regimes. So as we can see, there's a lot of similar patterns that you might expect when looking at any sort of low frequency variability in the Northern Hemisphere. You've got cluster 2 up here, and that's very similar to sort of a North Atlantic oscillation. You've got cluster 4 here, which is very similar to Scandinavian blocking. But there's also some novel features of these. And by identifying the events this way, you're able to see a lot more of the Rossby wave trains that are associated with this and just what might be stationary in other parts of the globe while the NAO is happening. So it's looking at a bit more of a broader scale feature, which I thought was good based on what types of patterns I was interested in identifying originally. For the sake of time, I will not be able to go through all 5 clusters through sort of like a time lag composite. So I'll be focusing here on cluster 5, mostly because that matches with the previous case study that identified as the longest lasting persistent ridge over North America. I wanted to dig into that a little bit more. So after this, I'll be showing quite a few series of time lag composites, and they'll be similar figures, so I wanted to go through those now. So on the left, you'll have 500 hectopascal geopotential height in the black contours. You'll have the height anomalies in red and blue contours starting at 40 meters. Statistical significance, again, through a student's t-test at the 95th confidence interval will be in the stippling stars. And to get a sense of perhaps some of the diabatic contribution, I also have plotted here integrated moisture flux convergence, which you get a sense at the column-wide diabatic heating that's occurring, and that's in units of watts per meter squared. On the right, I'll be showing the upper level jet, so looking at 250 hectopascal wind speed, starting at 30 meters in the black contours, wind speed anomaly at plus or minus 10 meters per second, again in red and blue, and that same integrated moisture flux convergence for continuity's sake. So if we look all the way back, so this is 10 days before I identify these patterns as being persistent. So it's looking at what sort of dynamics are occurring leading up to the persistence and what we can glean about the evolution of the patterns. So what we can see here, sort of cutting to the chase, is that there's this initial statistically significant ridge over Siberia, and that'll be a continuous feature that's there throughout the evolution of this time lag composite, and that seems to be some of the primary driver of some of the downstream flow evolution through downstream baroclinic development, which I'll be showing shortly. On the right here, you can see there's a few regions of jet anomalies, one here in the jet entrance region just off the coast of China, and one here in the Central Pacific near the jet exit region, as well as some here in the jet exit region just off the coast of Great Britain. If we step forward, we can see now that on the northern and eastern flank of this blocking high over Siberia, we can see that there's now a jet anomaly popping up at 10 meters per second. So that's indicative of stronger northerly flow and colder advection from Siberia that's entering the polar jet entrance region. So that's starting to increase the baroclinicity across the North Pacific. And you can start to see that reflected in the height field as well, as you're starting to get a statistically significant trough anomaly here just off the coast of Japan. If we step forward to 6 days before the onset, we can see that over the North Atlantic, there's these values of higher integrated moisture flux convergence that are associated with this developing ridge just off the coast of Canada in the North Atlantic. So that seems to indicate that if we're thinking about sort of the QG height tendency equation, that the diabatic contribution is helping to develop that ridge, and some of the latent heating along the storm track may be important here in developing the ridge here across the North Atlantic. If we step forward to 4 days before onset, we can see that doesn't occur over the Pacific Basin necessarily. We can see, is there an issue, Rich?
No, we just wanted to get the slide on back.
Oh, gotcha. Sorry about that. If we look here in the eastern North Pacific, we can see that the integrated moisture flux convergence is rather upstream of the height rises over the eastern, over western North America and in the far eastern North Pacific. So that indicates that there might be some slight differences between the ocean basins even as we're starting to develop this large-scale persistent flow pattern, that the ridge that's developing over western North America is not necessarily as closely associated with a diabatic contribution potentially. And here we are, it's only 2 days before the time of onset, and if I actually step back a few and focus here on the right panel, there's this initial jet anomaly here. Again, it's further west across the western part of the North Pacific. And as we step forward and you pay attention to that, you can see not only is the jet anomaly magnitude increasing, so you're getting a stronger and more extended jet stream, but all of this anomaly is now mostly in the jet entrance region. So primarily you have a very strong, slightly equatorward shifted jet stream across the North Pacific, and that's occurring as you're getting this large scale, zonally elongated trough in across the North Pacific in the mid-latitudes. And that's occurring as you're starting to get some higher latitude ridge development here along the Bering Strait. You've got the persistent ridge that's developed over western North America, and you still have hints of that blocking high over Siberia. And that's all starting to sort of come into play as these Rossby wave trains are emanating further downstream as well, and you're getting a lot more persistent features here in the Eastern Atlantic and over Western Europe as well. And by the time of onset of persistence, as I've defined it, we can see that the ridge over North America and Siberia have sort of merged together, or at least they're approaching each other as the anomalies span all the way across the high latitudes from central Eurasia all the way across to northwestern Canada and down through the western United States. Trying to look a little bit more holistically and perhaps a bit more objectively, I wanted to do some Hovmöller plots as well, just to get a sense of what the flow evolution was here as well. So here we've got time lag going downward in days in the same way that I had before. This is looking at the V wind anomalies of winds on the dynamic tropopause, average from 30 to 50 north here. As we can see, there's quite a few instances of downstream baroclinic development across much of the hemisphere. So you've got this periodic downstream wave train that's emanating mostly from the North Pacific Basin, so it's occurring at or further west of the dateline across the North Pacific. Excuse me. And it's occurring at an interval about every day and a half or 2 days. So it seems to be similar to that synoptic scale pattern that's happening. What's interesting is that this third and final sort of major wave train that emanates about 6 days prior to the start of persistence is the one that really gets things locked in across, across much of North America and into the Atlantic Basin as well. And a lot of this is from these wave trains that are interacting with and amplifying a lot of the stationary patterns that we're already seeing here, like this persistent ridge that's occurring over Western North America. What's interesting that is a little bit easier to see on the maps, I think, is that there's this rapid retrogression of a trough actually as the Rex block develops over the Central Pacific. So if I step backwards, You can see that Rex block forming up to 2 days prior, where you've got the developing ridge that is not statistically significant on top of the trough more in the subtropical and mid-latitude parts of the North Pacific Basin. And that's a very rapid process and part of how the regime actually develops in totality towards the end as it locks into the persistent pattern that's going to establish and continually sort of reinforce itself. If we now look at the higher latitudes to get a sense of maybe where that cold air is coming from, we can see that there are these periods of periodic cold air surges, and those are, again, linked to the lower latitude downstream baroclinic development. So if we look at these 3 circles and just step back, we can see that those are occurring just preceding the periods where you've got this strong downstream baroclinic development and the wave trains that are emanating across the North Pacific. So it really does seem like that antecedent blocking pattern over Siberia is a critical component to getting this entire flow regime set up, at least in the composite sense. What you'll also notice is that there's quite a bit more persistence here if we look at the high latitudes rather than the low latitudes or mid latitudes, but you can see evident of this final cold air surge or cold air outbreak across the western part of the North Pacific Basin is able to itself form a more clear wave train rather than having this larger scale dominating trough across the North Pacific that you can see here implied by the V-wind anomalies. So this is a very recent result that I wanted to just share with everyone and start to round out some of this analysis. So I've mostly focused on the mid and high latitudes. So like I mentioned in the motivation, I wanted to look a little bit more at some potential tropical influence here as well. So a lot of what we think about in terms of teleconnection patterns is through emanating Rossby waves through tropical convection that can propagate into the mid-latitudes and impact the flow pattern there. So what I've got plotted here on the top is actually the stationary Rossby wave number, which I've got the equations for down here. Essentially, it's just looking at what wavelength of Rossby wave is able to propagate and get a sense of the wave guidability of this of the jet streams primarily. And this is all essentially looking at gradients of absolute momentum along with the second derivative of the mean westerly winds. So this wave number here is calculated for the 10-day average of the U wind preceding the formation of the persistent flow regime. So exactly that same period of the time lags that I've been showing. And on the bottom here as well, I've got OLR anomalies here in watts per meter squared. Again, just trying to get a sense at where there might be potential convection that could impact the flow pattern. So as we can see here, there's a few areas of potential convection. So we've got this area of lower OLR anomalies over the western North Pacific in the tropical warm pool just off the coast of the Philippines. And we've also got this other area here in the eastern North Pacific and parts of the western Caribbean, sort of straddling Central America. What's interesting, though, is that you can very clearly see predominantly the subtropical jet is highlighted here in terms of the potential waveguide and where the Rossby waves are able to propagate. But what's interesting is, like I mentioned, there's an equatorward shifted and elongated jet. And because of the configuration of the jet entrance region in the central North Pacific, you can see that a lot of the Rossby waves, if they were to form in the western North Pacific, would be redirected back into the subtropics rather than being directed primarily up into the mid-latitudes where you can see a lot of the persistent flow regime developing. So that was interesting and sort of something to keep in mind for myself as I look at potential teleconnection predictability through things like the MJO and ENSO. But what you can see is over the Atlantic that there is this pathway for Rossby waves if they were to be forming here in just off the coast of Central America. They could propagate and interact with the flow pattern that was developing over Western Europe. So again, there's a bit of dichotomy here between the Pacific Basin and the Atlantic Basin that I think I'd like to keep in mind as I go forward. So just to wrap up here, these persistent flow regimes, sort of as a proof of concept, can be identified using a modified version of the persistent anomaly criteria, first defined by Dolan Gordon in 1983. By looking at the time-lag composites of cluster 5 of these persistent flow regimes, it suggests that primarily downstream baroclinic development from a pre-existing blocking pattern over Siberia is the governor of a lot of the eventual formation of the composite persistent flow regime. Like I mentioned before, the integrated moisture flux convergence values have slight differentiation between the Atlantic and Pacific, where they're maximized upstream of developing ridges in the Pacific and over North America, but they're largely coincident with ridges over the central and eastern Atlantic. So again, that suggests that further work is needed to understand this potential distinction through ocean basins that I also highlighted with the stationary wave number. Hovmöller analyses pretty much further emphasize the importance of downstream baroclinic development that can occur at various time lags in the composite of the formation of these patterns. And the stationary Rossby wave number calculation suggests that Rossby waves cannot propagate from the tropics to the extratropics in the North Pacific Basin preceding the formation of these patterns. So that's sort of an interesting thing in sort of thinking about the role of tropical variability that's typically happened at the subseasonal to seasonal timescale when trying to look at potential predictability. My email's down here, and with that, I'll take any questions. Thank you.
Hey, questions? 5 minutes of questioning, and we'll move on to the next. Jimmy?
So I think you talked mostly about the formation. Have you looked into how they break down these systems?
Not yet. Still have to do that analysis. In certain cases, I will note that typically what can happen is there's sort of like a out-of-phase baroclinic development where you might get 2 cyclones to form in close proximity, and that second cyclone no longer reinforces the blocking pattern on the upstream side, and that's enough to sort of break everything down as there's no longer that reinforcing mechanism to sustain the pattern. But I would need to look at the composites to make sure that showed up for a majority of the cases.
Oh, really interesting talk, Tyler. I was curious, have you thought about, or can you speculate at all about how these different clusters would verify? Do you think that there's one that's like, really difficult to nail down for the global or the models? Or?
Mm-hmm. That's a very good question. I think for the reason of it being such a good question, I've sort of put that off for after Albany. Mostly because I'm interested in seeing, what the primary mechanisms of variability are in the reanalysis, so it kind of pinpoints where to look in the deterministic models. But at least, again, from sort of ad hoc cases that I've noticed over the time, usually there's quite a bit of tendency to break down a blocking pattern too soon. And so some of that longevity, especially with some of these cases that can last, upwards of a month, I think that's a real challenge in some of these extreme cases at the tail end.
Okay, I think we'll move on to the next talk.
Thank you, everyone.
Let me, There's also University of Albany under the supervision of Lance Bozart. Alex has a broad interest in large-scale dynamics and variability. His goal is to enhance the prediction of synoptic scale phenomena and extreme weather on subseasonal to seasonal timescales in future research. Alex has a BS in meteorology from North Carolina State University. And after that, Alex went to University of Albany, where he has a master's degree examining the dynamics governing extreme precipitation events in Central America during the fall. And the title of Alex's talk is The Influence of North Pacific Large-Scale Variability on Recurving EPAC Tropical cyclones. Okay. It fell off. It didn't get printed on.
That's fine. Thank you, Rich. Yes, so today I will be talking a little bit more about the Pacific Basin, and in particular, I'm looking at the influence of, as Rich has already said, the North Pacific large-scale variability associated with recurving eastern North Pacific tropical cyclones. And again, I would like to acknowledge my advisors, Kristen Corbisiero, who loves EPAC TCs, and of course, Lance Bozard as well, for causing a lot of trouble. And I would also like to acknowledge the NSF for my funding. I couldn't help but throw this slide in last night. I woke up this morning and I went to breakfast and I saw in the news that this is something that's been going on primarily in the last couple of days. But as you may know or may not know, there's been some extensive and large wildfire activity over Hawaii, particularly over the island of Maui. And so far, there have been 36 confirmed fatalities from these wildfires. And throughout much of the news and throughout much of the NWS discussions, one of the key components or one of the key discussions I've seen so far is that you can see this a little bit in the GIF animation that I have here, but there was a strong easterly wind in the lower troposphere associated with a strong surface anticyclone to the north of Hawaii and the passing of TC Dora, which is tracking westward just south of the islands. And this is something that, again, has been alluded to and repeated multiple times, but I would encourage you to maybe look at this analysis a little bit more to maybe understand particularly what's going on in this particular scenario. I have some doubts and some ideas about what may be actually happening in this particular event, but nevertheless, this is something we could talk offline. So let's get back to the presentation. So TCs have many different types of impacts over the eastern North Pacific. And in this case, I'm going to be focusing a little bit more on recurving TCs, which can impact the mainland of North America. So a study by Corbisiero et al. 2009 looked at, in some ways, recurving eastern North Pacific TCs. And in their case, what they were looking at were TCs that happened to cross 25 degrees north and produce heavy rainfall over the mainland. And particularly within their study, they found that roughly 10% of all EPAC TCs within their given climatology from August 1st to October 15th from 1958 to 2003 brought heavy rainfall into the US. And particularly that frequency of heavy rainfall impact was maximized during September. Furthermore, they composited 20 TCs in which the TCs actually began to move poleward at lower latitudes and again, were able to bring heavy rainfall over the north or over the southwestern US. And in this particular figure I extracted from this paper, at the onset in which the TC crossed 25 degrees north, you could see within the composite analysis that the primary feature that showed up within these particular TCs was an upper tropospheric trough just to the northwest of the TCs on average, and a weakened subtropical ridge over North America, which allowed the poleward motion of these TC tracks overall. Another study by Wood and Ritchie in 2014 actually looked at the extratropical transition of EPAC TCs. And one reason I wanted to just quote and cite this paper particularly is because most of the TC tracks within this individual paper showed a similar type of distribution of TCs either moving poleward or actually recurving far east as well in the basin. And what they also found in their study, and at least at the time of extratropical transition, was the presence of an upper tropospheric trough as well, just to the northwest of the actual TC center. And so this was something that motivated me from the literature at least to understand, is this the primary pattern that we should expect to see overall TC impacts and recurvatures in this part of the basin? And I want to actually kind of zoom out a little bit too, and from a different perspective. This was a study by Camargo et al. 2008. And what they wanted to do in this particular study was to describe the overall TC variability. And one of the reasons I wanted to cite this paper is because they use a probabilistic clustering technique to look at all TCs from 1966 to 2013. And they divided these up into 3 different clusters. And you can see in cluster 2, this largely reflected many of the EPAC TCs that either recurved inland or produced probably more likely heavier impacts over the western US or western North America. And similarly, they found that one of the most novel results from this study was that cluster 2 particularly was shown to be significantly associated with the westerly phase of the MJO, which is something we should also consider on these intra-seasonal timescales as well. So one of the main motivations is from my anecdotal perspective. When I came into graduate school in 2018, this was something that was going on as soon as I entered grad school. And of course, this was something that our research group was also talking about at the time as well. But this was a phenomenal year in which you had many TCs that were able to recurve or move poleward and cause some heavy impacts. And you could kind of see that here in the latter half of the TC season based on the overall distribution of these tracks plotted. And one of the TCs, of course, that caught my interest immediately was Tropical Cyclone Sergio. And this was a recurving EPAC TC that made landfall in Baja, California. And in terms of the impacts, it led to about $2.67 million worth of damage, and mostly this was due to severe flooding further inland. And you can see here, this is published, or this is a source from the WPC at the time, but they had a 24-day or 24-hour outlook of the rainfall issued over the region. You could see at the time there was some heavier rainfall or pockets or confined areas in which we were expecting to have heavy rainfall. And sure enough, later on in the observations, we found that places like Phoenix, Arizona, were able to break some of their own records for the given month. So I highlight the entire month in the prior slides of the TCs because it wasn't just TC Sergio at the time. There's other TCs that also made landfall at the time. But nevertheless, to this day, this was still the wettest October on record, and they received about 5.35 inches in Phoenix, Arizona, which is about 70% of their total rainfall for the whole given year. So these definitely have some large impacts, not only from a damage standpoint, but also just from a water cycle standpoint as well. So I'm going to highlight some of these TCs because I think this is something that we actually should look at a little bit closer detail before I make any too many summaries or too many conclusions. But nevertheless, TC Rosa and TC Sergio, these were back-to-back systems in the later part of September and early October. But these are the two primary TCs that I'll actually draw on a little bit more in the terms of this case study. And I point out TC Olivia. You might notice that this is not a recurving TC. Well, it's for good reason, because this system actually plays a larger role downstream in the WestPAC. So there's often times where EPAC TCs can cross over the date line. Usually they'll dissipate, but there are all times where they remain intact, and some of their remnant precipitable water signatures can still be traced even on a map. And of course, there was a Central Pacific TC that recurved and actually underwent extratropical transition. We'll see why this matters actually in terms of how this affected the EPAC TC tracks. And finally, if we go further west in the WestPAC TCs, there was typhoons Trami and Congreve, both of which recurved and also underwent extratropical transition as well. So what I want to do now really quickly, and I don't want to spend too much time on this, but I wanted to go over the overall flow evolution of this in the spirit of kind of like a map discussion kind of style of looking at this particular case. So here what I have plotted is the 3 to 200 hectopascal layer average PV, which is in the gray contours. You have the irrotational wind vectors plotted in the arrows and the quivers there. And in the red contours, this is signifying the 6 to 400 layer average hectopascal ascent, and followed by the 250 hectopascal jet, which is shaded in the cool colors. So when we begin in the September 24th, 2018, one of the things that I noticed immediately within this particular case was that Typhoon Trami, which is located here just south of Japan, makes its way, or at least remains fairly quasi-stationary in its earlier lifetimes. But nevertheless, as this system begins to move poleward, it undergoes extratropical transition. You could see the irrotational wind vectors in the form of outflow impinging on the North Pacific jet. And so what ends up happening is this North Pacific jet becomes enhanced, it amplifies, builds the localized ridge, and then you lead to downstream formation of a trough over the Central Pacific, which you see highlighted here. But before I get ahead of myself, if you look just to the EPAC, you see TC Rosa that's then steered inland as well before making landfall sometime around October 2nd or 3rd within this particular timestamp. But before that, again, you see that this going back to the Central Pacific, you see a cutoff low that forms in response to the extratropical transition of Typhoon Trami. And what gets picked up here, if you remember correctly from the Central Pacific TC, is Tropical Cyclone Walaka. That system then begins to undergo extratropical transition as well. And you can see the remnants of that precipitable water make its way further north, associated with this other trough that develops just downstream of Typhoon Congreve, as that is also making extratropical transition. So finally, you get this large-scale ridge that forms in response to the typhoon that undergoes extratropical transition, the WestPAC, and then the Central Pacific TC Walaka. And what ends up happening inevitably is TC Sergio, which is now located just over here near 130 degrees west, then begins to remain quasi-stationary as it's tracking westward, and then deflects northeastward in time here, as you can see within this particular these timestamps. So what I wanted to do in terms of the motivation of this case is maybe to describe how often is this a particular type of scenario in which we should expect in a given TC season, or maybe in other words, is it an outlier? So just to go back to the presentation, wherever that is at. There we go. All right. I wanted to quickly just show like an overview of how I imagine, I just really quickly wanted to show an overview of how I would describe this overall variability for this particular case. But the main drivers in this case are the positioning of the anticyclonic wave breaking that you get downstream over the central and eastern North Pacific. But in this case, many of this, this amplified flow pattern was also further enhanced by TCs undergoing extratropical transition. So this is something to note of an importance. So the first question I wanted to address potentially, motivated a little bit by Camargo et al.'s paper, is to understand what are the unique distributions of TC tracks throughout the EPAC region, just from a climatological or historical perspective. And I take a similar approach because I want to be able to describe overall TC variability before I dig too much into the details of recurving systems. So the way I do this is I adopt a k-means clustering type approach, adopting a technique from Nakamura et al. 2009. And essentially what I wanted to do is take into consideration the overall track shape, length, and location in terms of how you would cluster these. And so I take these two mass moments down here along each individual TC track to understand not only the centroid of the TC track, but also the variance of the actual directions of the track along the way as well. And I weight that by the individual wind speeds at 6 hourly inputs from the NHC HERDAT. And so the TCs that I consider here are from 1951 to 2020, and these are all plotted in black contours. And on the top right-hand side of this figure, you can see that I've plotted in a bar graph form of the temporal distributions of all the TCs within this climatology. And you can see there's a relative maxima or peak around August and then around September, but you can see that the overall PDF is centered near August. But when you do these k-means clustering without any information about the temporal distribution, this is what the 4 clusters look like of all the TCs I just showed in the previous slide. And I'm going to zoom up a little bit so you could see it closer. But nevertheless, you could see that there's large differences among the track type when you use this type of approach. And if I zoom into cluster 1, for example, you find that cluster 1 contains the most samples within the overall distribution. And again, the TC distribution temporally is pretty uniform, I'd say, with a relative maxima near September. But the characteristics of these TCs are primarily tracking westward, usually typically towards 130 degrees west, where they begin to either dissipate or weaken, or you do have some that typically track along the North American or the Mexican coastline and even make landfall in certain cases. Cluster 2 depicts more tracks that primarily track westward, but if you maybe not notice right away that TC Sergio was one of the systems that actually became classified within this overall distribution given its track length. So I thought that was pretty interesting. You might be able to actually point it out right here in the map that TC Sergio, as it was tracking westward, became influenced by the overall large-scale steering, and that, in this case, made landfall in Baja California. Cluster 3 looks somewhat similar to what we saw in Cluster 1, but the biggest difference is the latitudinal extent. Most of these TCs typically cross at least 20 degrees north and typically do not move much further west, but I would consider this more so the poleward moving or the recurving type cluster characteristic of the overall distribution. You could see, similar to what we saw with the Corbicio et al. 2009 study, that there was a relatively maxima in the TC days within this given distribution. And then finally, cluster 4 depicts 41 TCs in this case that generally move westward, but they typically can maybe have more impacts over Hawaii, for example, or move poleward once they move over towards 150 degrees west. And this is a peak that we typically see around July or August. So scaling back and looking at all the overall clusters, thinking back in terms of recurving TCs and their associated impacts, I wanted to focus a little bit more on clusters 1 and 3 in this particular case. And so what I want to do is extract the recurving systems to see how representative of what they look like within the overall distribution. So to extract EPAC TCs that recurve, I wanted to define a recurvature of the TC direction that changes from westward to eastward while also moving poleward at the same time. And the recurvature point that I'm going to assign is the farthest westward point reached by a given TC. And this has to, this is the first occurrence of the most westward position during the consecutive 6 hourly intervals. And of course, if TC undergoes multiple recurvatures, I then take the most westward position during its last recurvature to utilize as the onset of that. And the TCs would have had to at least reach tropical storm intensity at least once during their lifetime. So from cluster 1, if you extract the TCs from that given cluster, you'll see that most of these systems, either if they're recurving, they're typically either equator of 20 degrees north, or they usually make, if they do make landfall, they're typically over Baja California, like southern Baja California, or over Mexico. And if you look at cluster 3 in this particular case, you can recall that these systems typically move a little bit further poleward. In this case, a lot of them generally make landfall in Baja California, or even maybe their remnants track into the southwestern US. And tying these together, you have about 91 TC samples that are extracted in terms of recurving systems overall. So what I wanted to do is maybe characterize these a little bit in terms of the large scale variability and looking at the overall distributions as well. So if you look at these recurving systems from both clusters, again, it shouldn't be too much of a surprise that these systems typically peak in occurrence around September and even into October. The TC status among all the recurvature points in these clusters are typically a tropical storm status. And then, of course, you have some that are generally with a hurricane TC status or intensity, and then you have about 13 out of the 91 samples that are of a tropical depression type status. And if you look at this from a climatological perspective over a longer time series, you could see that throughout the entire distribution, there's some relative maxima in this type of activity throughout from 1951 into 2020, and you see some of this recorded prior to the major satellite era into terms of 1966 to 1970, and you see maybe some secondary maxima later afterwards into like around 2006 to 2010. So some of that I want to be able to dig in a little bit more to understand particularly why this particular subset of years were much more frequent in this case. But again, given the our limited information prior to satellite era, it could be quite challenging. So one of the things I want to do, of course, thinking back to the title of this talk, is to see what the representative large-scale flow patterns look like among these recurving systems over the North Pacific Basin. So one way we can do this potentially is to describe the overall environmental variability, is to implement self-organizing maps using the ERA 5 reanalysis. And what I wanted to do is I utilized a North Pacific domain using the extracted TC recurvatures from clusters 1 and 3. And I qualitatively picked a 3x3 size SOM matrix and utilized 500 hectopascal geopotential height standardized anomalies to conduct this SOM analysis, again from 1951 to 2020, representing the TC climatology. And here's a visual kind of way of how I explain this type of SOM framework. But what I did was I extracted, as you saw, the recurvature points from each individual TC case, and I took a snapshot essentially, or extracted the timestamp associated with that across the entire North Pacific Basin. And then I here organized all those individual timestamps into a 3x3 SOM matrix. So when you do that and you utilize the 500 hectopascal height fields, you get a representation that looks like this. So starting from the top left into the bottom right, you can see that from nodes 1 through 9 that there's, in general, from I would say maybe 6 or 7 out of the 9 nodes that are listed here, you can see that there is a presence of an eastern North Pacific trough. Granted, some of them having different types of tilt and magnitudes. But there are some cases, especially if you look towards, let's say, nodes 3 and 6, where you don't really see necessarily a strong eastern North Pacific eastern North Pacific trough, but you do see some evidence of a trough further upstream, which again is slightly, I would say, far removed from where most of the TCs were recurving, which was near southern Baja California. And if you look at it, if you look at the North Pacific jet type structures, or you look at the 250 hectopascal wind speeds, which are in the shading, and the MSLP, which is in the contours here, you can clearly see that there's large jet variability as well at the onset of the time in terms of the strength of the North Pacific jet and how it may or may not be interacting with TCs as well. So in order for us to just save a little bit of time, since I'm running out, I wanted just to focus on a couple of nodes for the sake of this talk. I wanted to look at particularly nodes 3 and 7, and in this case, it's these two. And the reason I picked these two is one, node 3 particularly has a large-scale ridge that's enhanced over British Columbia with a trough upstream. And then in the case of node 7, which is on the bottom left corner, you see a signal of a ridge development maybe towards the Gulf of Alaska and in a trough, or Eastern North Pacific TC, or Eastern North Pacific trough that we see in the composite analysis from earlier studies. So what we're going to do is actually do a time-lagged composite, similar to what Tyler just did in his presentation, but we're going to start 5 days prior to the onset of TC recurvature. And in this case, and within nodes 3 and 7, 5 days prior, you see some slightly different signals within just the geopotential height fields, which I have, again, plotted in the contours and shading and anomalies. And then one of the main features that I noticed with node 3, for example, is that you have a central Pacific trough that appears over on node 3. Whereas on node 7, you don't really see a central Pacific trough. You maybe, if anything, you start to see a ridge beginning to form over the eastern North Pacific. And then you see, again, a much stronger North Pacific jet relative when you compare from 3 to 7 as well, for node 3 specifically. But if we step forward in time to a day minus 4 T minus 96 hours, you could see that from here to here, you see on the Western Pacific over node 3, an enhancement and development of 2 upper tropospheric troughs that leads to further development by minus 3 days or minus 72 hours. And again, what's interesting about this is that you could see that the jet builds from west to eastward in node 3, whereas in node 7, you kind of see what looks like a weakening and an actual enhancement or development in the upper tropospheric trough near British Columbia, as we saw going into the onset. And then finally, what's interesting about this as we get into days 2 and minus 1, particularly leading up to the onset, you can see a completely different distribution of the overall variability or overall geopotential height field here, where you have a strengthening of the ridge over the EPAC in node 7 and a strengthening of a ridge over British Columbia node 3. And what I think is going on here is this trough begins to deepen over the EPAC in node 7 versus in node 3, is that you see changes or differences like we saw in the 2018 case of where you have enhanced anticyclonic wave breaking. And I think that's helping to at least understand some of the partitioning as to why you can have a case in which TCs are able to recurve with the presence of a trough or lack thereof. But the point of this is that when you look at it from the steering flow and you look at it from the PV framework, you can kind of get a little bit of an understanding as to maybe what's going on. So that's what I'm going to show here. Is in these 2 plots, it's the same nodes, but in this case, I'm just looking at the 150 hectopascal layer average PV, and the contours are representing the same thing, which is the PV itself, followed with the wind barbs associated with that layer average as well. And one thing you can note is that, again, you see the ridge, you see the differences in the trough and ridge couplets among each of these 2 particular nodes. But I would argue that in some of these cases, you can get enhanced anticyclonic wave break-in that leads to PV streamers that can also manifest themselves as upper tropospheric troughs and lead to inland steering. And there's also times in which the trough or the ridge itself can develop and create a quiescent flow environment near the TC, and then you can get these beta drift type scenarios where the systems are still able to move poleward, and maybe towards the end of their lifetimes they can become steered inland if a short wave is able to propagate underneath the ridge, or if it has some interactions with the subtropical jet. So I'm just going to leave my conclusions here just to go over, but what we did, particularly within this early part of my work, is to use a k-means clustering to kind of give us a good, unique spatial distribution of all EPAC TCs and understanding what their clusters represent, not only temporally, but also physically too, which I want to be able to conduct going forward. And then within these particular clusters, I noticed within clusters 1 and 3, you typically had a 500 hectopascal trough centered over the EPAC, but there was often times where shortwave troughs were able to undercut a larger scale ridge that formed in the same place. It could still interact with TCs. But overall, I think that there's a lot more work that I want to be able to do. I think there's some suggestion that the North Pacific jet variability might be tied to some of these TC cases, and also looking at other teleconnections potentially as well. And so with that, I'd like to thank you for your time.
Okay, questions or comments? Questions or comments? Let's see. So this tendency to curve to the north, is that almost always a beta drift, or is it almost never a beta drift?
I think it really just depends on the genesis point and into the proximity of the actual landmass itself. This was a study done in 2004 by the author here, Sanson, and they looked at a barotropic model using a simplified barotropic model to understand if you were to place a vortex within this particular, and you can see how they did 9 experiments here. If you were to place a vortex at each of these different spots, how would the TCs migrate minus anything else, minus anything about the large scale variability? And generally what they saw is that most TCs tend to drift northwestward, and that's typically due to the interactions with the overall topography itself. But there are cases, in many cases, in which this drifting occurs first, but then something in the large scale helps to further steer it inland. But there are certain cases historically where that might not always be the case too. So that's something I want to help, maybe hope to partition in some way by further evaluating the steering flow locally.
Okay, so northwestward is sort of the default, and then something else has to make it go.
Yeah, and in this particular study, they look at the contributions of the planetary drift versus just the topographical contribution, then they combine it in the experiment. Okay. And depending on which latitude you're at, that poleward motion might actually change depending on its proximity to the land and latitude as well, based on Coriolis. So, yeah, there's a large sensitivity in terms of genesis point within this particular study.
It's also, Baja is very hot. And maybe not this time of year, but but I think it is very hot.
Yeah,
so
it is.
Does that play any role in the heat low and everything?
I would say so. And honestly, the weakening of the subtropical high is really the most common pathway in which you can get these types of motions. Otherwise, you're impinged by the low-level easterlies induced by that, because you can't get any other upper tropospheric feature to steer it out. So, like the opposite direction, that is.
Yeah, makes sense. Okay, here we go. Now, this could be another question to be answered in the distant future.
Thanks. Also, super duper interesting too. These are both really great. So I was kind of curious. Even some of the cluster that had the most curvature, in the the most storms that were doing the eastward curvature. I'm not a hurricane person, so I'm gonna butcher some things, I'm sure. Do you have any speculation of because even within that cluster, there's a lot of variability on the severity of the curvature. Like any speculation on what drives, kind of within the cluster, like how much?
Yeah, I mean, I have definitely some speculation in terms of what might be going on. I mean, I would certainly speculate the most that the systems that drastically recurve poleward or even inland are probably within this distribution of the time in terms of the peak. That occurrence is generally probably around September. These systems that generally maybe track more westward or maybe along the coastline, they probably are more early season phenomena. But I would still have to show that or evidence that. But that's my speculation based on just the recurvature extraction alone. But yeah, that's a great point. I think also too, you have to consider that when these TCs move northwestward, typically they'll enter an environment of high vertical wind shear and cooler SSTs, so they tend to rapidly weaken in many of these cases. But there are some cases, especially in El Nino years, where they're able to maintain its symmetry and remain intact before landfall. But yeah, that's a great point. Now, again, I want to be able to spatially explain these from a physical perspective too, going forward, and seeing how much of an outlier these recurvings really look like within the overall distribution.
Okay, I think we are at the end of the formal part. Thanks again, both
Thanks.
speakers. And please join us for refreshment and continued discussion in the hallway over here.